Okay, good morning. Today is our lecture number 6. We are in the process of learning fundamentals of mechanical vibration. And today's topic is damped free vibration. So far, what we have seen is simple harmonic motion, and that is undamped free vibration. And we were able to get the response or the solution in many different forms. But essentially, they are harmonic functions. Essentially, they are sine waves or cosine waves. So, or their combination in the compact form. So, when you say vibration, there are three important things that has to come in your mind. That is, one, the frequency of vibration. Number two, the amplitude of vibration. Number three, the phase angle of vibration. So, if we have these three information, then we are able to best express or explain the vibration characteristics of any system on its natural vibration. So this is what we have learned, and today we are going to look at importantly other vibration type called damped free vibration. Again, it is free vibration, that is its natural vibration, right? So what is the difference between undamped free vibration, damped free vibration? In undamped free vibration, we have considered so far an important vibratory elements, the spring and mass, the elasticity of the material and the mass of the material. So a component can be modeled to be a spring and its lumped mass. And then the vibration of that can be in one directional, single degree freedom it is called. And that is what is that we have looked at. And the response x of t can be given by harmonic function. Right, so there are many mechanical systems where we can witness such kind of vibration induced, and they would be naturally vibrating on their own. For example, simple pendulum vibration. So that is vibrating naturally on it. So you just give the initial disturbance, and then it will ever vibrate, and the pendulum clock is operating on that principle. And then if the motion is executed by not by disturbance, also if it is by an external other harmonic function or any other type of function, and then it is what is called forced vibration. So we will take the forced vibration later in our lecture series. And today's class we are going to look at again natural damped vibration called damped free vibration. So along with the spring and mass, we are going to introduce an element called damping element or damper. Right? So what is damper? So damper is neither a mass or elasticity that it represents. So it is element which is going to dissipate energy. So the vibrational energy of the system is getting dissipated in the form of heat or sound is what is called this damper. And the damper would be dissipating energy if at all there is a relative velocity of its ends of the damper. So this is what something that in the first hand to say about damping, we are going to get into our class. Let me share my screen. Hope you are able to see the screen. And this is that last lecture what we have seen. I'll just quickly browse through and then get into today's class. So what we were doing in the last class is undamped free vibration. Undamped free vibration, and we have derived the response for that. You see here we have spring and mass element alone, and you know that the energy, vibration energy means what? So at the static equilibrium position, the energy is 0 and it is static condition. Then you give an initial velocity there, you get a kinetic energy at static equilibrium position. That makes this block to move down, and then it come back to here and goes up. So when it goes and then it is coming back from its extreme amplitude position is because the kinetic energy which is impinged onto this mass at the start is getting restored as a strain energy in the spring or vibration energy in the spring. So the entire kinetic energy is converted into vibrational strain energy, and that strain energy is maximum at its extreme position. And because of that, there will be reverse motion that is called the point of reversal. And then the available strain energy or the potential energy called is getting converted into again kinetic energy, and that becomes again the same amount of kinetic energy with which it started. And because of that, the direction of the motion is in this side, that kinetic energy pushes this up, and then it becomes completely potential energy and so on. So at the mean position, you have full maximum kinetic energy. At the extreme position, you have only potential energy. In between, you have combination of both of the energy. However, the total energy remains constant for a conservative system. That is why we call that natural vibration as undamped natural vibration. But in reality, any vibration, if you look at it, it cannot be undamped free vibration because there are resistance for the motion of this mass, especially the air resistance. Or if you look at in any mechanical system, the reciprocation of this is not resisted by fluid around the system. So, for example, reciprocation motion of piston inside the cylinder of IC engine. So, you look at there, you have that motion where it has been resisted by fluid. So, you have resistance in the form of air, fluid or solid element. Then you have the energy dissipation, and that is where the modeling of damping that comes into picture. So, today's class we are going to learn about that aspect of natural vibration. So this is lecture number 6, and today's date is 13/08/2021. And today's lecture topic is damped free vibration. So when I say damped free vibration, let us understand what is this damping. So how do you define damping? So damping is the mechanism with which the vibration energy is gradually converted into heat or sound, and that is what is called damping, right? And the damping can be of different types. So it is difficult to determine this cause of damping in practical systems. And damping is modeled one or more of the following ways. So how the damping in the practical system can be modeled. So let's just have a background of damping, then get into vibration motion. So the damping can be a viscous damping. So what do you mean by viscous damping? Let's discuss. When a mechanical system vibrates in a fluid medium, such as air, gas, water, or oil, the resistance offered by the fluid onto the moving body is what is called viscous damping, and that is why the energy getting dissipated. So it is primarily going to depends on what are the factors. It is going to depend on vibrating body size and shape, and it's going to depend on the viscosity. It's an important property of fluid. The viscosity property of the fluid, the frequency of vibration, and the relative velocity of the vibrating body. So this is all going to decide how much is amount of energy that will be dissipated in the damped vibration. So the viscous damping is the one which is referring to the resistance offered by a fluid. Air can be liquid or it can be solid medium. And the damping force, if you look at, so it's directly proportional to the velocity. And the proportionality constant is what is given by a damping coefficient. So this is what is called a damping coefficient. Here. And this damping coefficient unit would be Newton second per meter. Right? So now, how do you derive this damping coefficient is what we have to look at it. Right? So can you just say the examples of typical viscous damping elements in the mechanical system? That will be fluid film between sliding surfaces. Any sliding surfaces you see between them, you have a fluid film that can represent viscous damping. A fluid flow around the piston in a cylinder is what is viscous damping effect. And fluid flow through circular orifice can refer to a viscous damping. And fluid film around the journal bearing, you see that are the typical viscous damping examples. This is on one side, if you look at. And how do you find now this damping coefficient? That's what to understand. Let's look at this system now. So we have two plates. This is one plate. There is another plate. Out of these two plates, this plate is say fixed on the ground. It's a fixed plate. And this plate is moving plate, and this is being separated by a fluid film. It's separated by a fluid. So let's call this as fluid between them. Now the motion of this plate, of the top plate, is in this direction with the velocity, say, u. So the velocity of plate to this direction is velocity u. And this is fixed. And this is separated by the fluid. And now if you look at the fluid in contact with the moving plate would have the velocity same as that of the velocity of this plate. If that is so, the fluid in contact with the fixed plate will be stationary there. So the fluid would have the motion as this plate goes related to this fixed plate, and the fluid can be imagined as the layers of fluid, and in every layer would have its velocity. The top layer which is in contact with the plate would be with the same velocity u. The bottommost layer of the fluid is in contact with the fixed plate will not move at all. And the variation can be imagined to be linear variation. So let's look at the variation like that. If this is the variation, so my velocity now would be what? And the velocity here would be same as velocity u, and then the velocity would be linearly decreasing. So this is the velocity profile of this fluid as the plate is relatively moving with reference to the fixed plate, and the layers of the fluid motion is this. And this fluid is what is the viscous fluid that has got some viscosity. So the plate height, let us see now here. From here, it is at the height of h, its position. And you know this velocity here, whatever is represented, is directly proportional to this velocity here is going to be varying as function of x. And that is what is the function of this distance that's varying linearly. So you will have velocity gradient there. Right, so let us now define what is damping force here. So the damping force F would be equal to, or there is a shear stress into the area of contact. So this is what is the damping force. So how do we get that? So for that, let me just explain here this variation. So the variation can be looked at as this u velocity is u by h is what is equal to any point the velocity by y. So what I mean by that, if I consider from here at a distance y, a fluid layer, the velocity of this fluid layer here is say v. Then v by y is what is u by h. I get this linear relationship, right? So from this, I get now an elemental fluid film at a distance y. I look at its velocity v. If that is so, its velocity v is given by u into y by h. Right? And now, why do I have this is to define what is shear stress in the fluid layer. So how do you define shear stress in the fluid layer? And that is where you understand Newton's law of viscous fluid. Viscous fluid. So what does that states? Newton's law of viscous fluid states, it states that shear stress between the layers of fluid. Because see, the shear force, by the way, what we are interested in to find out what is the direction of shear force at this point, it would be in this direction, opposite to this motion. So this is my shear force, and that would be given by shear force coefficient into x here, x dot, and that is going to be here equal to C into small v, C into small v. So I have to get, just a minute, I'll write it clearly. This F is going to be C into small v. So small v is on a layer, fluid layer at a distance y from this fixed plate, and that would be given with this relationship of the top fluid velocity at this upper plate velocity. So if that is so, Newton's law of viscous fluid state that the shear stress at any layer would be proportional to the velocity gradient du by dy, du by dv by d. Here it's v, so dv by dy. So this is velocity gradient. So that proportionality constant is what is given by property of the fluid called viscosity. So mu times dv by dy is what is shear stress. So the shear stress in a fluid layer is function of velocity gradient, and the proportionality constant here defines viscosity of the fluid. And that's given by Newton second per meter square unit. Right, so if you have that in hand, then I can come back to this writing the damping force. So the damping force is tau into A, and here shear stress is mu times the velocity gradient, mu times dv by dy into A. That is the shear force at this layer. So if I have to write what is the shear force at the topmost layer, then it would be equal to mu into v. This would be replaced by v by y into h. V by, is that correct? V by h. So it's going to be either V by h or
So U by H.
V by h, or it is mu times U by h, right? U is the topmost, so I can have it like that. I can rewrite this expression. See, this we have to be careful here, right? This is linearly varying. So in the topmost layer, you get your velocity would be v into h by v, h by. So this velocity of the plate is given by v into h by y. That's there here. So if I have to write my shear stress expression, it is a shear stress expression is given by this, and hence if I get a force, I will have substituting this over here, mu into u, that is v by h into a, right? And this from this I can combine. I'll take this v out with the v or u. I just change the notation at the beginning. So this is u. So this is u, right? U by h. So I would have now mu a by h into u. That's what is F at the top of the plate. That is damping resistance offered to the plate is what is given by this, and this is what is now defining C into U. So where C here is what is called damping coefficient. Damping coefficient, right? So this is how you can define damping coefficient. There can be problem with this data that can be solved in the examination if it is asked. And then let's go ahead looking at other two forms of damping present that can also be offering not the resistance alone, is the kind of dissipating medium, right? So what are those? So one is the dry friction damping, or it's called Coulomb damping, where that is going to be having constant force in magnitude, but opposite in direction. It would act always against the motion of the body, and it is caused. See, yeah, and it is caused by a friction between the rubbing surfaces that either can be dry or it is insufficiently lubricated. And such cases that damping is called Coulomb, Coulomb friction damping or dry damping. You also have another damping type called material or solid damping. Material or solid damping. Solid damping. So material or solid damping, how do you understand? This is also called with another interesting name, hysteresis damping. Hysteretic damping. Hysteretic damping. So how do you understand when material is deformed, any material body is deformed, you see that the energy is absorbed and dissipated by the material. So we see that vibration is due to rigid mass, but you can also see the vibration due to deformation of the mass. For example, you see the tire vibration. Tire vibration can have vibration as a rigid mass without any deformation. Tire vibration can also be looked at a vibration due to deformation of the carcass part of your tire. So that would be flexing. So that is a deformation. So the deformation also can cause vibration. In such kind of thing, the damping present would be what is called solid damping or hysteresis damping, where this damping also can be intuitively assumed to be damping with the viscosity. So hyperelastic material definitions and so on for rubber material vibration is concerned. So that all go into tire side when you have to account damping. So that's what you can witness when you are touching the tire of your vehicle at the hot sun. That would be with the higher temperature. When tire is interacting with the road and goes, there is vibration, there is an energy dissipation continuously that is coming out of your tire. And that is what is all primarily due to this solid or hysteresis damping, where the vibration about its mean position will be under loading and unloading continuously. If this is not with an elastic limit and slightly against, then there will be a loop formation that can be witnessed if you look at the stress strain diagram of that. And the mechanism of this solid damping is that relative motion between the planes forming the solid, the molecular structure. So there will be a relative motion of the material planes, and that is what is causing this kind of damping effect called material or solid damping, and they are also dissipating. So when you say the word damping, dissipation. So you always remember. So the dissipation is what is the work of any damping nature of the material. So how that stress strain diagram would be appearing for material damping. So if the material undergo deformation, that absorb energy and dissipate it. So you see that I have stress on y-axis and strain on x-axis. I can also have, instead of stress, force here. and deflection or deformation here. So either stress strain or force or deflection. And you see that the hysteresis loop is something this. So this would be in a loading cycle and then it is an unloading cycle. So the area in this loop is what is the energy that is dissipated, and that is what is that is what is that energy that is dissipated. So how do you get this energy dissipation understanding? So look at now again graph. I'll take here strain and stress, and let me take this cycle represented from here. That goes here and then comes back. It is not smooth bending, it is going sharp, that like that it will come. And let's name this point as A and this point as B, and this point, projected point here down D, and this point as C. So if you look at in this ABD, the area under this ABD, entire thing, is what is called energy expended. Energy expended. And if you look at the area inside the loop, under the loop, here alone, this energy alone. That is area BCD, BCD. So separating this, and if you look at this area BCD, this triangular area, and that is that energy dissipated. So this one, the blue color, what is there? That is BCD is what is called an energy recovered. That is energy recovered. Energy, just a minute. Okay, expanded and the energy dissipated. So this is the energy. Some 1 minute, just a minute. Energy recovered is what is given by BCD. Energy expended is given by ABD. So this is what is energy recovered energy. Correct. Energy recovered. So how do you get this energy expended? It's nothing but work done. That's nothing but work done in a given cycle. One cycle of this loading cycle would be given by small u. That's work per cycle. Work done per cycle would be given by your stress into d epsilon. So what is this stress into d epsilon? It is an elemental. It is an elemental step that has been taken on this with the height of E. So that's stress at this level, and then with this difference of elemental strain d epsilon. So integrating this over this area is what is going to give me work done, and that is energy expended per cycle. That's given by integral E into delta epsilon. So this hysteresis loop for elastic material, if you look at, it would be like this, right? So if you go in for hyperelastic material, then there is something called more involved viscoelastic nature and so on. So become more material modeling, where you see you have to understand what are called the constitutive model and so on. But we are not going to discuss at the moment. We're going to just look at the material elastic, and then there is rubbing of intermolecular planes, then the energy can be dissipated, and that is what is kind of solid damping. And that to understand during cycling, that means deformation about its mean position of a solid would be expressed by energy expended per cycle, and that's what is given by this. And what is the energy recovered is this. So the red one in this zone is what is the energy that is dissipated. So if you get the energy expended, and you can get this area which is recovered, and the remaining energy would be the energy which is dissipated. And that is because of the damping property. So with this understanding of a bit of damping, damping itself is more researched topic, and we have textbooks for them to understand. And we are getting into our vibration study, free damped vibration. So now what is that our vibration model going to look like? It is not only a spring and mass model. I have this mass. So it is not only the mass attached to the spring, also you have now a damper element. And the damper element, most of the time in vibrational case, assumed is viscous damper. So when it is viscous damper, it is mainly through the viscosity of the fluid, and of course the shape and size of the vibrating body, and so on. So here the spring is characterized by the spring constant. Similarly, the damper is characterized by damping coefficient. How can we define and find out damping coefficient is what we have just finished discussing. And if this is your vibratory element, and that it is under static equilibrium position, this is a static equilibrium position. That means this attached here, there is a force that is preventing it to move, but it is pulling it, and it is taking it stationary position. So the damper also will offer the force as this started moving. So there is a velocity at the end of the damper. So there will be a damping force. So if this is its mean equilibrium position, and free vibration can be excited by means of giving initial velocity, or pushing it to an extreme position or any position, leaving it, giving an initial displacement, we can execute the motion. So the same way what we discussed is applicable here. And then this is going to vibrate with reference to the static equilibrium position. And that vibration is not going to continue forever, that what we have seen in undamped free vibration. It's going to dampen out. It is going to die out. So how the response of the vibration system would be now is what is our keen looking forward to learn. So for that, let me draw free body diagram of this mass to get my motion governing equation. So here that would be two forces acting on this. So one is the force due to spring, that is going to be K into X, and another one is C into X dot. And that is what is going to be equal to the governing effect force, as this motion down is considered positive, and that's going to be now in this, and that is M into X double dot. So taking this convention, I would be able to write my governing equation minus Kx minus Cx dot is what is equal to Mx double dot. So this side is positive, this side is negative because of this reference. So this is going to be Mx double dot plus Cx dot plus Kx, that's going to be 0, is what is the governing equation of damped free oscillation. So this is equation number 1 for damped free vibration. Damped free vibration. So now, how are we going to solve this? For that, I can consider my trial solution. I'm going to take the trial solution with the Laplace variable, what we have seen in the last class. So that is, so my trial solution would be x of t is going to be c e raised to st, and here c and s are unknown constants, arbitrary constants, and not constants. See, in this is variable, s is variable, c is some unknown variable. So that can be predicted now. Before that, let's just substitute x of t is equal to this into this equation. So for that, let me find out what is x dot of t. That's going to be c s e s e raised to st. X double dot of t is going to be c s square e raised to st. And substituting that in 1, what is that I would get is c s s square m s squared c e raised to st plus c into so this c and this c don't get confused here. C, if I substitute this as c raised to st plus k into c e raised to st, and that's going to be 0. And if I take this c e raised to st out, it is going to be ms square plus cs plus k into c e raised to st. That's equal to 0. C e raised to st is x of t. That cannot be 0. C e raised to st cannot be 0 to satisfy this equation. So what can be made 0 is ms squared plus cs plus k is what is equal to 0. And this equation is a polynomial equation or a quadratic equation called characteristic equation of the damped free vibration. So the roots of this characteristic equation is going to give you an interesting aspects and help you to get your response. The roots is what it's a quadratic equation. So you know quadratic equation roots s1 comma 2 can be written as minus b, so minus c plus or minus under root of b squared minus 4ac. That's going to be c squared minus 4 into m into k divided by 2a. So 2 into m. So these are the two roots, and these two roots can be written now in a convenient form. So let me take this 2m inside, take it to a numerator. So it's going to be c by 2m plus or minus the root of c squared by 4m square minus this 2m goes inside, so it's going to be 4m square, and 4m by 4m goes off, it's going to be minus k by m. Right, so this is my roots s1 comma 2. So having now the roots of this variable s, I can write my solution in this way. So I'll have two solutions x1 of t, as I have got two roots. That's going to be one is c1 e raised to s1 t, another one is x22 of t. That's going to be c2 e raised to s2 of t. And then substituting this into this, you know, this is linear vibration model, and the governing equation on the other side it's 0, so it's a homogeneous ordinary differential equation representing this. So the solution total response can be addition of these two, x1 of t plus x2 of t. So principle of superposition is holds good in a linear system. So I can simply add these two, and that is going to be my total response. And substituting for this here, it's going to be c1 e raised to, in place of s1, it's minus c by 2m plus under root of 4 by 2m, c by 2m square minus k by m So this all into this S1 into T plus C2 e raised to minus C by 2m minus within bracket C by 2m whole square minus K by m. This all into T. So that's what is my X of T. And you see here, I have C1 and C2, and these C1 and C2 are arbitrary constants, can be determined from the initial conditions that we are very much familiar with. So before getting into that, let us look at again another interesting definitions that can make this in very compact form. That's what is called the critical damping. So we have learned what is damping, and we'll introduce what is called the critical damping. And another one is called damping ratio. So now let's look at what is this critical damping. So the critical damping is the value of damping when the radical sign in this root is going to be 0. So if that is to become 0, C by 2m whole square minus K by m equals to 0 when I say this C is going to be Cc. That's called the critical damping. So I represent critical damping by C subscript C. So if this is 0, your root is going to be what? C1 e raised to minus C by 2m T. So this is going to be 0. That time the damping here, the C would be Cc by 2m. So C1 e raised to minus Cc by 2m plus C2 e raised to minus Cc by 2m. If I write into, of course, into T, if I write, I'll get the vibration called a critical damped vibration, critically damped vibration. So that is where you define this critical damping. So when you make that statement there like that, and this is going to be equal to 0, that's going to give us the estimation of Cc square. So Cc square here is going to be, this goes on the other side, that's K by m, and this here goes 4m square. So I can rewrite this as now 4km by 4km, and then Cc is going to be in the root of that. That's going to be like this, right? So let me rewrite this once again instead of writing it like this. Instead of writing it like this. So let me write my Cc now. This way. Under root of this all, so let me have this K by m as it is. That's because under root of K by m omega n, you know, so I will be able to write in terms of natural frequency. So it's going to be 2m omega n. Why? Is because it's going to be 2m under root of K by m. So root of K by m is omega n, and you get the critical damping is 2 times the mass of the vibrating system into natural frequency of the system is what is critical damping. So if we have critical damping defined like this, so you can define another interesting factor called the damping factor. Damping ratio or factor it is called. So let's call this damping ratio, and this damping ratio is given with the notations like this. This is damping ratio, and that is defined as C by Cc. So the damping coefficient of the system to that of the critical damping, the ratio is what is damping ratio. And this can be understood from here like this. So C by 2m, C by 2m is what C by 2m can be rewritten as C by Cc into Cc by 2m. So I just have Cc by Cc. So I just put it. So this is the definition of zeta, and Cc by 2m is what? Omega n. Cc by 2m is omega n. So I can rewrite this as zeta omega n. So C by 2m is zeta omega n. So my roots can be now written as, S1 comma 2 can be written as 2 by C by 2m, so that's minus zeta omega n plus or minus under root of this is going to be C by 2m whole square. So this is going to be zeta square omega n square minus k by m. So that's going to be omega n square. So like this. So in this, if I take my omega n out, it's going to be minus zeta plus or minus under root of zeta square minus 1. So this is ending here, this radical. Into omega n. This omega n is common here, it's taken out and it's gone there. So this is my two roots, S1, comma 2. So now what is my response going to be? I can rewrite my response x of t as C1 e raised to, instead of that S1 root, I will put this root. It's going to be minus zeta plus root of zeta square minus 1 into omega nt. So earlier we had C1 e raised to omega nt like that. So now this factor comes here. Plus C2 e raised to minus zeta minus the radical zeta square minus 1 into omega nt. Omega nt. Right? Okay. We can write it like this. You can also write now, continuing with this, I can rewrite this in this way. Right. I can rewrite this in this way. So this is my response. So I can look at now 3 different cases based on my damping ratio value. So if zeta
one doubt,
is
sir.
not, yeah.
So in that equation, minus zeta plus or minus root of zeta square minus 1, right? Can't we take zeta out of the root? Zeta and minus 1 out of the root?
No, it is inside root. No, see, in the root of this. Where is that I have taken out?
No, I'm asking, can't we take it outside the root?
This
Can
one,
we?
if you are taking it, then it is 1 by zeta square will be there. Why do you want to do that? So if you are taking zeta square out, it's 1 minus 1 by zeta square out. So this is very convenient and popular forms you would see in the textbooks, right?
Okay,
We are going to write it this way. So I'm going to explain you what is the significance of this, right? Just to give me a minute and we'll get to know. So now the zeta damping ratio we define so that we can classify the 3 different cases of vibration. So one is if zeta value is not equal to 0, that means you would have C by Cc some value, right? So the zeta value normally vary from 0 to 1 for an underdamped system. So that is called underdamped system. If C by Cc is equal to 1, what is that meaning? Zeta value is 1. So we define zeta value as C by Cc. If that is equal to 1, the damping in the system is critical damping. So if your damping is less than 1, so if I say this is equal to 1, then C is equal to Cc. And this is what is called a critically damped system. This will not have any vibratory motion. So that we'll see from the response. So this is case 2. This is case 1. So you can also have C by Cc greater than 1. So you can have zeta value greater than 1. That means C by Cc is going to be greater than 1. And that time it's called the over damped system. So this is case 3. So let us now look at, we'll just keep them aside and look at the case 1. What is zeta value is equal to. So when zeta is equal to 0, what will happen? Look at if fourth case, before going to that, if zeta value is equal to 0, what is that? It is undamped system. So the natural vibration, what we have studied, would holds good. So when it is going to be 0, C by CC ratio, C numerator should be 0. So C0 means what? Damping coefficient 0. That means in our vibratory system, there is no dissipation. So the system can be assumed to be conservative system. It will have only spring and mass element. Like that you can say. And then whatever we have learned so far, all could be generalized now from this. So in this solution, if you put zeta 0, look at what is that is going to be. It's going to be x of t equals C1 e raised to. So zeta 0 here, it's going to be minus under root of minus 1 omega nt. So it's going to be I omega nt plus C2 e raised to. See again here, this is going to be minus I omega nt. So this is nothing but what we have discussed in the last class, the response solution. So again, we have made this into a compact form and so on. So this we have already dealt with. So this portion is already we have dealt with. And now today's class, we are going to look at the case 1, what is called an underdamped system. So this is what is called an underdamped system. Underdamped system. So we have another 5 minutes. I will end the class. You can go to the next period. So to understand this underdamped system, let's look at our roots once again. S1 comma 2. That's going to be minus zeta plus or minus. Now I rewrite it like this: I into minus root of 1 minus zeta square. So zeta squared minus 1, I have taken minus 1 out. So under root of minus 1 is I. So I have here complex conjugate part. So I into this into omega n. So this is my root. So now my response x of t is going to be C1 e raised to S1t. So that's minus zeta plus I minus 1 minus zeta square into omega n t plus C2 e raised to S2t. That's going to be minus zeta minus I into under root of 1 minus zeta square into omega nt. So this is my response. So I can look at here again. I have a real part. I have an imaginary part. Then I know how do I work with this, right? So I can take the exponential part, real part out, e raised to minus zeta omega nt. See, if I take omega nt inside, it's minus zeta omega nt plus this term. And e raised to that, I can split and the product. This, if I take it out common, I would have inside C1. And again, I will group C1 and C2 coefficients are common, C1 plus C2 into cos of 1 minus zeta square omega nt. This is outside the radical. Please be careful. Plus I into C1 minus C2. See, this is analogous to what we were doing it in the last class. Sine root of 1 minus zeta square into omega nt. So this is my, this is closed. So you see, this is taken out an exponentially decaying function out, and then you have this. If you look at this, you can see the C1 plus C2 is one constant, and this is C1 minus C2. So to differentiate from undamped vibration, I will call this a C1 C dash, and this is C2 dash, right? So I'm going to have my solution e raised to minus zeta omega n t into C1 dash, which is C1 plus C2 cos of, I will just rewrite this. Instead of writing it in this radical form under root of 1 minus zeta square into omega n. So look at this part alone. I'm going to call that as omega d. That is damped natural frequency. So I'm just going to rewrite now my equation as cos omega dt omega dt, omega dn you can put, or d subscript n. Some book it's only omega d is written, so you can take this plus C2 dash I into sine omega d t. That's my response x of t. So in this C1 dash and C2 dash are arbitrary constant can be determined from the initial condition. So if we have this, you can see exactly this is similar to what we were discussing for an undamped system format. Only element additional here is this exponential function. So I can rewrite this expression also in another form. I'm not going to discuss that. I leave it to you to experience it as x naught e raised to minus zeta omega n t. See, look at outside it's omega n. Inside only it's omega d. Omega n t into sine function of omega dt plus y naught. So with a reference to phase angle also we can write. Or we can also represent this cosine function as x e raised to minus zeta omega n t cos of omega dt minus phi. So these all are the three forms of the response of the system. And here, make a note of it, and that is the last point of the lecture. And omega d, what we defined as under root of 1 minus zeta square into omega n. Omega n. So omega d by omega n, omega d by omega n is under root of 1 minus zeta square. 1 minus zeta. One minus zeta square, right? You can look at this graphically as what is the variation of this ratio as function of zeta can be looked at like this. Let me take on y-axis. This is going to be omega d by omega n, and zeta on this. So if that is so, I would have this as a quarter circle. Because if I square on both sides and if I take this on this side, it's going to be circle equation. So the value here is 1, value here is 1. So when zeta is 0, sorry, here omega d by omega n is 0 on this axis, right? How do I say zeta axis? Omega d by omega n 0. How do I say this vertical axis? Zeta is 0, I'd say. So this is my center. So if I say this omega d by this is 0, I'll have zeta 1. If I say zeta is 0, I'll have this 1. So this is how I can represent. And for any value, why do I have to take from 1 to 1? Because zeta 1 is corresponding to zeta 1 is corresponding to this corresponding to C by Cc equals 1. That's critical damping. So anything within this, if I take any value, and what is the corresponding value of this, I would be able to get. So when omega d by omega n is 1, what does that meaning? It is zeta 0 damped system, the undamped system. So this is to represent omega d by omega n to represent undamped system, and zeta equal to 1 to represent critically damped system. And anything between this value of zeta and you'll have omega d by omega n less than 1, because omega n is greater than omega d. So you would see that is how you can remember this equation. And this will be in always the question in an interview or many examination, competitive exam, you'll see based on this problems can be solved. Just to stop at this point of time, because we may have to go for the next lecture, and let us look at this response, how does it graphically appear and so on in the next class. And then we will get into quickly to the forced vibration. There are many aspects of forced harmonic vibration and that we have to learn in our course, right? So if you have any doubts, I would answer. Otherwise, I'll end the lecture at this time. Is there any doubts? If no doubts, I'll stop.